Good morning. Hello and welcome. In this session, we are diving into one of the most exciting shifts in artificial intelligence, the rise of AI agents and the protocols that makes them work together. You will hear about the Model Context Protocol or MCP, often called as the USB-C of AI, which lets agents connect to tools and data. Then we look at the agent to agent protocol or A2A, enabling AI agents to collaborate much like teammates in a group projects. Then we will go on to understand the agent communication protocol or ACP, a powerful standard for multi-modal sharing of text, image, video and audio. Then we will try to understand the Agent Network Protocol or ANP, a backbone for decentralized global agent ecosystem. But it's not just about what these protocols are. We'll also explore the real world challenges that face on a daily basis, from security risk to trust issues, and the checks and balance we can put in place to make them safer. Finally, I'll walk you through 10 case studies spanning healthcare, finance, disaster response, education, supply chain, and smart cities to show you how these protocols can transform our world. By the end of this video, you will understand not only how this protocol work but also why they matter and how they could form the foundation of the agentic web, the next internet powered by AI agents. So, whether you are a student or a professional or just curious about the future of AI, stay tuned. This video is for you. Good morning. This is your host, Savit Vittal Salian. Let's start the learning journey. The agenda. Artificial intelligence is evolving from being just a tool that answers questions to becoming a active participant in our digital ecosystem. The rise of AI agents are autonomous, proactive systems capable of reasoning, decision making, and collaboration marks a profound shift. Unlike earlier AI, which only responded to prompts, agents initiate actions. They work together with other agents and integrate with digital infrastructure. This transformation is called agentic AI. To make it practical and safe, the AI world is now standardizing protocols that govern how agents communicate, collaborate, and integrate. Similar to how HTTP, SMTP, and TCP/IP standardize the internet. This video explores AI agents in depth, the emerging protocol ecosystem like MCPs, A2As, ACPs, ANPs, and how they shape the coming agentic Web. So, what is an AI agent? Well, an AI agent is a system that perceives its environment. It processes context using reasoning or machine learning models. It acts autonomously towards its goals and learns and adapts over time. Analogy is, think of a personal assistant in real life. If you ask a human assistant to book a flight, they don't just give you airline website. They compare schedules, check the cost, apply your preferences and confirm the booking. AI agents aims to do the same, handling tasks end to end. AI agents are system built on AI, especially the large language model or LLMs that can act autonomously, make decisions, process context, use tools, and achieve goals with minimal human inputs. They are not just generative chatbots, they are proactive, capable of adapting based on feedbacks and environment. Let's look at the journey from generative AI to agentic AI. Generative AI, example the chat GPTs that we know about, great at answering questions, generating text and images. Agentic AI, well, it goes further. It's autonomous, goal driven, integrates various tools, collaborates with peers, and can take initiatives. Example, instead of asking ChatGPT for the best project management tool, an agent could research all the available tools in the market, compare their features and pricings, and draft a recommendation report, and even set up a trial account on your behalf. So that's agentic AI at play. Well, let's go in summary. What's agentic AI? Well, this refers to a new generation of AI systems that pursues objectives independently, handling tasks by reasoning, learning, and coordinating among peers. Instead of fixed response, they manage workflows, collaborate across boundaries, and scale intelligently. It's a foundational shift in how AI functions. So, why agents need protocol? Well, without common standards, each agent is locked inside its ecosystem. Agents can't talk to each other. Tool integration becomes custom and fragile. Analogy, imagine if your every phone maker had its own charger. That's the current state of many agent systems. Protocols like MCP are the USB-C of AI agents. So, why protocol matters? Well, just as USB standardized device connections or SMTP standardized emails, Autonomous AI agents need protocol to discover capabilities, communicate securely, coordinate tasks, integrate tools and data reliably. Now, the absence of such standards can lead to siloed or fragile systems. Hope this helps with a certain perspective. Historical foundations. Long before modern LLM based agents, research in multi agent systems explored agents' communication. There are a few. We had the knowledge query and manipulation language known as KQML. These are early agent languages developed around 1990s. Then we add PIPA ACL or Foundation for Intelligent Physical Agents, agent communication languages. These were standardized agents interactions with defined semantics. Then we had Contract Net Protocol or CNP, a marketplace model where agents bid for tasks like freelancers. These early systems were mostly academic, but they built the conceptual bedrock for today's AI agents protocol. Transition to modern AI. Well, with LLMs like GPTs, Claude, Gemini, the agents gained the natural language reasoning, the multi-model understanding, and tool use capabilities like APIs or plugins. They gained memory and long-term planning. But to scale globally, these agents need internet grade communication standards. Let's look at the core protocols for agentic AI. MCP or Model Context Protocol was introduced by Anthropic in 2024, was quickly adopted by OpenAI, Microsoft, Google, and others. It acts as a standardized interface for agents to connect with external tools or APIs or database and knowledge source. We use JSON RPC over HTTP, meaning it's lightweight and universal. MCP is like an electric plug socket. No matter what appliance you bring, as long as it fits the standard socket, it works. GitHub's integrated MCPs, allowing AI agents to pull repo data or run code checks and submit pull request without needing custom plugins from framework. From a security perspective, MCP must defend against prompt injections and malicious tool behavior. Companies like Microsoft are already adding safety layer into MCP integrations. So that's MCP at the top. Let's take it from another angle. It's a MCP is a universal open standard developed by Anthropic, released in November 2024, now widely adapted. It acts like a USB-C port for AI models, giving agents a consistent way to access external tools and data. Could be file systems, APIs, messaging systems, or JSON's RPC 2.0 via HTTP or S2O. MCP supports multi-tool workflow, IDE integrations, knowledge base access, internal enterprise systems, and dynamic environments like cloud desktops, GitHubs, Wix, Zotero, and more. OpenAI integrated MCP into its agents SDK, ChatGPT, desktop, and APIs. Google's DeepMinded Mind plans support via upcoming Gemini models. Microsoft added MCP in its Copilot Studio, Azure, GitHub, Windows ecosystems, including security focused integration. From a security consideration perspective, prompt injection risk, tool spoofing, and multi tool attacks have been raised by security researchers. So that's MCP. Agent to agent protocol, or A2A. This was proposed by Google in 2025, now governed by Linux Foundation. It focuses is agents discovering, authenticating, and coordinating with each other. That's the focus of A2A. It enables task delegation between agents like research agent for collecting data, summarization agent for condensed finding, reporting agents to prepare the final deliverables. A2A is like LinkedIn for AI agents. It lets agents introduce themselves, verify identity, and collaborate. In enterprise customer service, one agent handles, say, email intakes, another agent queries database, and a third writes the response. A2A ensures this smooth communication. As mentioned, developed A2A was developed and announced in 2025 by Google. It's now under the Linux Foundation for Open Governance. It enables agents to discover, authenticate, coordinate with each other's ecosystem. It uses a client server model, enabling discovery of capable agents and secure task delegation. So that's A2A for you. Agent Communication Protocol, or ACP. Well, it was developed by IBM's BI, which is now part of Linux Foundation. It's optimized for rich multi-modal communication. It includes the text, audio, video, streaming. It's useful in collaborative workflow. Example, agents working on design, media, or simulations, where you require a lot of collaborations. ACP is like your WhatsApp for AI agents. Not just text but also attachments, multimedia, and real time conversation. Example, in healthcare, one diagnostic agent shares the MRI image and its analysis with another which is treating or planning agents using ACPs. As mentioned, ACP was introduced by IBM BI, which is now governed by the Linux Foundation. It enables messaging between agents and tools, often via REST, supporting multi-modal responses and streaming. It's useful for collaborative and asynchronous workflows requiring rich communication format. Agent Network Protocol or ANP. It's a protocol which is open, decentralized agent ecosystem. It uses decentralized identifier, in short, DIDs, and JSON LD knowledge graph. In this, agents can negotiate the roles, negotiate services, and trust across domains. ANP is like the internet's DNS system, allowing agents to find and trust each other globally. Example, in supply chain logistics, ANP allows agents from different companies, whether it is shipping, warehousing, insurance, to interact securely without a central control. So, ANP supports agents' discovery and collaboration in a decentralized network using decentralized identifier and JSON LD graphs. It consists of three layer structure. First is identity and secure communication. Second is protocol negotiation. Third is application level interaction. It enables an open agentic marketplace, connecting agents across domains. So that's ANP. So let's look at how this protocol works. MCP analogy is it's like a USB-C socket. A2A is like LinkedIn for agents, peer communication. ACP should be thought like a WhatsApp, that's for communication between. ANP is decentralized. Analogy is the DNS or the for the agents. The MCP uses external systems. ACP is multimodal and streaming. A2A is task outsourcing, and ANP is the open agent ecosystem. You can pause the screen and take a screenshot if required to, if that helps you with your own internal work. So, how do you go about it? Yeah, what should be your potential strategy? It should be layered. To adopt this, you start with MCP for tool integration. Then you add ACP for rich communication. Then you use A2A for multi agent collaboration. Finally, you scale with ANP to build a agentic marketplace. Now, MCP for tool integration. Just recollect or refresh the table that I shared earlier. MCP is your USB-C socket. That's integration. ACP for rich communication, which is your WhatsApp. A2A is for multi-agent collaboration, which is your LinkedIn type example analogy. And then your ANP, which is your DNS as an analogy. Just do remember this flow and you can bring down your strategy on these lines if that works best for you. Think through what works for you. Let's look at some case studies. From BFSI sector, the MCP is used for securely fetching customer account details. As an example, A2A is used for fraud detection agents to collaborate with compliance agent. ACP, the multilingual chatbot streams voice and text for customer services. ANP is used for cross-bank agent negotiating settlements in trade finance. These are examples. The usage is far wider than this, but this gives you an idea, a perspective on where these individuals would play a role. In healthcare, MCPs is used to connect to electronic health record. ACP is used to share patient imaging data with AI diagnostic agent. A2A used as doctor's assistant agent, delegating to insurance approval. Basically, that's an interaction between a doctor and insurance companies. ANP, well, agents across hospital networks share research findings securely using ANP. When you come to telecom, for network monitoring, tool integration, because there are many tools which would come into play in this space, MCP is the one which is used as a base. For troubleshooting agents collaborating on fault detection, that's your incident management, event management space, if there are agents on that, that uses A2A. For cross operator roaming optimization by autonomous agent, that's when you have areas serviced by some other provider and you are from a different provider. To have that conversation in between, ANP is used. When you go for from an e-commerce perspective, MCP is used to pull inventory and shipping API data. ACP for conversational shopping assistant, which is required to interact with multiple interfaces. ACP is used. A2A is primarily used by delivery agent to collaborate with warehouse agents. And ANP is used for interlinking the marketplace agents from different vendors. When we look at it from a challenge and risk perspective, from a security perspective, the prompt injection or malicious agents and data poisoning are real challenges. There's a risk around that. From trust and identity perspective, agents need verifiable credentials. From interoperability perspective, competing standards may fragment the adoption. We'll look at this specific as we move forward. But interoperability is the key here because you have so many different type of agents by different manufacturers. Having that interconnection is key for success. From an ethics and governance perspective, autonomous agent could make harmful decisions. From a scalability perspective, billions of agents interacting requires a robust infrastructure. How that is going to be is a challenge that need to be addressed. Now let's look at from a future of agentic web perspective. It's expected by 2030, billions of AI agents could operate like today's web browser. ambiguous, interoperable, and essential. The agentic web may replace apps. Instead of opening 5 apps, you will direct your personal agent, which will negotiate across others. From a protocol perspective, you have MCP, A2A, ACP, ANP, which will be foundational as TCP/IP and HTTP is for web today. They are likely to be the foundational protocols. Just as the internet grew from static web page to today interactive apps, the next leap is an agentic internet where agents run the show. Now let's go with individual case studies. We have 10 case studies for this video. The idea here is to get clarity on each of the topics. Let's start. The first case study is on the model context protocol, that in software development automation space. Well, in modern software engineering, development team often juggle multiple tools. Could be GitHubs for code repositories, Jira for issue tracking, Dockers for containerization, Jenkins for CI/CD pipelines, and Slack or Teams for communication. Traditionally, integrating these platforms require custom APIs, plugins, and significant overhead for maintenance. Every time a new tool was added or updated, developers needed to write new connectors or modify existing ones. This created friction, delayed releases, and reduced the productivity of engineering teams. The Model Context Protocol or MCP changes this landscape by acting as a standardized interface between AI agents and external tools. Think of it as a USB-C port for software tools. So once a tool supports MCP, any AI agent can plug into it without bespoke development. In a developmental environment such as Virtual Studio Code, an AI powered coding assistant could leverage MCP to seamlessly access GitHubs or Jira or Dockers and testing frameworks without requiring individual plugins for each station or systems. Here's how it plays out in practice. A developer is writing a new feature on VS Code with the support of an AI coding agent. The agent noticed that the code may introduce performance risk based on previous similar commits. Using MCP, it retrieves recent commits and comments from GitHubs, analyzes related Jira tickets for context, and checks Docker's build logs for error tied to similar models. All of this happens through MCP's standardized JSON RPC integration, which ensures smooth, consistent data flows. Next, the agent creates a pull request on GitHubs, automatically linking it to a Jira issue that it also generates to track the change request. Now it runs a Docker's container build to ensure there are no dependency conflicts, and even notifies the team in Slack that a new build is ready for review. Instead of navigating 4 or 5 separate tools, the developer works entirely inside the VS Code, while the AI agent manages integration via MCPs. The impact is significant. Developers save hours that would otherwise be spent on context switching or tool hopping or manual integration. Teams experience fewer error because MCP provides standardized, structured communication between agents and tools, thus reducing any misconfiguration. The project timelines accelerate because AI agents can proactively manage repetitive tasks like ticket creation or log monitoring and build validation. Now, from a strategic standpoint perspective, organization gain resilience because the MCP based approach is future proof. As a new tools emerges, they can be connected to the ecosystem without rewriting the integration. This modular, standardized architecture lowers long-term maintenance cost and support scalable DevOps practice. On the security side, MCP also introduces challenge. For example, if a malicious prompt injection convinces an AI coding agent to delete repos or alter build pipelines, the standardization of MCP could amplify the damage. To mitigate this, enterprise must wrap MCP use in guardrails such as role-based access control or enable audit logging and agent sandboxing. Microsoft integration of MCP in Copilot Studio already incorporates such security layers, thus ensuring enterprise readiness. In short, MCP in software development automation demonstrates how a single interoperability layer can transform productivity. By removing the need for custom integration and enabling AI agents to fluidly manage tools, MCP paves the way for a new generation of agent powered DevOps workflow. This case study highlights how MCP bridge human creativity with machine efficiency, making the software development cycle faster, safer, and more collaborative. Let's now take a look of MCP implementation to the second case study. Now, in this case, we'll take a case study of health record integration. So, healthcare systems are notorious for their data silos. Hospitals often use multiple platforms for electronic health records, or laboratory information system, or pharmacy database, or imaging tools, and insurance portal. Now, each of these platforms speaks its own language, making it difficult for doctor and staff to access patient information in one unified view. As a result, clinicians waste valuable time switching between systems, which can lead to delays, inefficiencies, and sometimes even medical errors. Now, here comes the MCP. The Model Context Protocol or MCP provides a way to breach this silos. By standardizing how agents connect to different systems, MCP ensures that an intelligent healthcare assistant can seamlessly fetch and merge information across platforms. For example, when a doctor queries, show me all of patient's eggs, lab results, and current medication, the AI agent uses MCP connections to pull data from the lab systems, from the pharmacy database, and the EHR or the electronic health record space. The response is compiled and presented in a structured, readable format inside a single interface. That's what the AI agent would do using MCP. Now, if you look at from a practical workflow, lab integration, the agent receives the blood test results from the lab systems. Using MCP, it accesses the pharmacy database to list active prescription. Then it fetches recent radiology scan from picture archiving and communication system or PACS. The agents correlates this data to highlight interaction between medication and the lab values. For doctors, the time saving are immense. Instead of logging into multiple systems and cross referencing data manually, the agent does the legwork in seconds. From a patient's perspective, it means faster diagnosis, fewer errors, and better continuity of care. On the strategic side, hospital benefits from reduced integration cost. Traditionally, healthcare IT department would have to build custom connectors or use expensive middleware to link their EHR with labs or pharmacy systems. MCP now reduces that need by providing a plug and play interoperability layer. This flexibility is particularly useful in multi hospital network or in partnership between hospital and insurance companies. So, security, however, is a key concern here for sure. Healthcare data is highly sensitive, and MCP driven agents accessing multiple systems could introduce risk of unauthorized exposure. To address this, MCP implementation in healthcare must incorporate role based access control, should have audit trails, should enable encryption and compliance with regulations like HIPAA or DPDP Act are required to be done. Now, hospitals adopting MCP can also sandbox agent action to ensure that AI does not mistakenly alter or delete patient data. In a sense, MCP in healthcare record integration demonstrate how agentic AI can act as a medical assistant, not replacing doctors for sure, but giving them the right information at the right time. By unifying fragmented system into a single AI driven view, MCP improves patients' outcome while reducing system inefficiency. The result is a safer, faster, and more intelligent healthcare delivery model. Case 3, using Agent Communication Protocol or ACP. This is about legal case preparation. Well, law firms handle vast volume of documents which include contracts, evidence, transcripts, precedents, and client communications. Preparing a case often requires pulling together multimodal content. Could be written legal briefs, scanned images of evidence, audio from witness recording, and even video depositions. Traditionally, paralegals and junior lawyers spend weeks compiling this material manually. This slows down the preparation and increases cost for the client. Here we have ACP entering the equation. The Agent Communication Protocol or ACP addresses this challenge by enabling AI agents to communicate seamlessly across multiple formats. Could be text, could be audio, video, or image. ACP is like a multimodal messaging standard for agents, allowing them to exchange rich content in a structured workflow. In a law firm scenario, three specialized AI agent could collaborate: the research agent, the evidence agent, and drafting agent. Now, research agent is used for pull relevant legal precedents and status in text form. The evidence agent would process, scan, document audio and video from discovery. The drafting agent uses research and evidence stream to prepare a structured legal brief. The Agent Communication Protocol or ACP provides the standardized channel for these agents to share information asynchronously, much like colleagues chatting on WhatsApp or Slack, but with formalized data structure. Now, here how it plays out in practice. Say a lawyer asks the drafting agent to prepare a motion. The drafting agent uses ACP to request case laws from research agents. Simultaneously, it requests deposition transcript from the evidence agent, which streams the text and tags videos highlights over the ACP. Once it receives the material, the drafting agent compiles them into a professional motion document and notifies the lawyer. The benefits are significant. Lawyers save countless hours of manual collation. Client gets faster turnaround on legal document, and firms can handle larger caseloads without proportional increase in staff. Moreover, ACP ensures that content shared between agents remain synchronized and complete, thus reducing the risk of oversight or any omission. The risks center on confidentiality and data leakage. Legal firm deals with sensitive documents, and if an ACP message stream is intercepted or mishandled, it could compromise a case. Now, to mitigate this, firms deploying ACP must have an end-to-end encryption, a very strict authentication, and legal data compliance standards need to be maintained. Agents should also be restricted from external data sharing unless explicitly authorized. So, strategically, ACP positions law firms to adopt AI first legal operations. It enables multimodal collaboration among agents, providing lawyers with comprehensive case files in record time. Instead of being bogged down in administrative work, lawyer can focus on strategy, advocacy, and client interaction. This not only improves legal outcome but also makes legal services more affordable and accessible. Now let's take a second example of from ACP side of it. This is about remote education. Well, the shift towards digital learning has transformed how teachers and students interact. Online classroom now include not just video calls but also digital whiteboards, real-time quizzes, chatbots, and translation tools. However, these systems often function in isolation, forcing teachers to juggle multiple platforms while trying to keep students engaged. This fragmentation creates barriers for learners, particularly those with diverse needs, such as student requiring translation or visual aids or requiring any additional tutoring. Here comes ACP. The Agent Communication Protocol or ACP can revolutionize remote education by enabling seamless multimodal collaboration among AI agents. ACP allows agents to exchange message that contain not just plain text but also images, diagrams, video snippets, subtitles, and real time data streams. In an online classroom, multiple specialized agents could work together. It could be the tutoring agent, or a translation agent, or a question and answer agent, or an engagement agent. Example, explaining complex topic with interactive diagrams and math questions. That's what a tutoring agent would do. Providing live captions in multiple language for international student. That's what a translation agent could do. Handling real-time student question via chats or freeing the teacher to focus on instruction. That's what a QA agent could do. Or conducting quick polls, quizzes, and feedback surveys. This can be done by the engagement agent. Now, to understand, let's look at how it works in practice. So, a teacher, suppose, explains the concept of Newton's law during a virtual lecture. The tutoring agent sends an animated diagram of a ball in motion over ACP to the classroom platforms. Now, a student in Brazil will view subtitles in Portuguese provided by the translation agent, while another in Japan reads Japanese subtitles. All of these synchronized in real time. Meanwhile, the question answer agent answers side questions in the background chat, and the engagement agent runs a short quiz on gravity at the end of the session. All of this communication flows smoothly via ACPs, thus ensuring that the agents share and stream content in a structured and synchronized way. The benefits are substantial. Teacher can focus on pedagogy while agents handle repetitive or technical support tasks. Students experience inclusive learning, whether they are struggling with language barriers or need visual reinforcement or benefit from instant feedback. Schools and universities gain scalability, enabling one instructor to effectively engage hundreds of students with personalized support. The risk, well, however, it revolves around data privacy and academic integrity. ACP driven learning agent often capture classroom interaction, which could raise concerns about surveillance or unauthorized data use. In addition, agents answering question might inadvertently provide incorrect or oversimplified information, potentially confusing the student. Now, to address this, ACP implementation in education must emphasize accuracy, content moderation, and compliance with privacy regulations such as GDPR or the current India DPDP Act. Strategically, ACP empowers school to build next generation classrooms that adapts to students' need instead of trying to replicate physical classroom online. ACP enables a richer multi-model experience that may actually exceed the traditional model in inclusivity and personalization. Over time, this could make education more accessible, affordable, and engaging across the globe. Agent to agent protocol, or A2A. Let's take a case study of customer service automation to understand this better. Customer service has always been a resource intensive function for organizations, especially in highly regulated industries like banking. Customers expect fast, personalized service. Yet, behind the scene, multiple checks, which is identity verification, fraud detection, compliance validation, must happen before a simple request can be fulfilled. Traditionally, these checks were handled manually by call center staff, thus resulting in long wait time and high operational cost. Here, A2A enters the scene. The agent to agent protocol provides a way to automate these processes by enabling specialized AI agent to collaborate and delegate tasks seamlessly. Unlike MCP, which connects agents to tool, A2A connects agents to each other, allowing them to coordinate workflow as peers. In a banking customer service scenario, three specialized agents could work together. Could be customer support agent or the KY verification agent or a fraud detection agent as an example. There could be more. Now, the customer support agent interacts directly with client via chat or via voice. The KYC verification agent validates the customer's identity using uploaded documents or biometrics, whereas the fraud detection agent monitors transaction patterns for any suspicious activity. Now, let's understand how it works on the flow. So, a customer contacts a bank asking to increase their credit limit. The customer support agents engages with the customer and via A2A delegates the identity check to the KYC agent. The KYC agent verifies the customer's document in real time and reports back. Simultaneously, the support agent asks the fraud detection agent whether the customer has any high risk patterns. Once both the agent confirm, the support agent approves the request. Or if fraud risk is flagged, it would escalate it to a human manager. All this coordination happens automatically through A2A's secure agent to agent messaging. Now, the benefit is clear. The customer receives faster, more consistent service, while the bank reduces the burden on human agents. Specialized AI agents ensure that compliance and fraud checks are not overlooked, thereby reducing the regulatory risk, if any. The modularity of A2A also means that banks can plug in new agents, say a credit scoring agent or a loan eligibility agent, without redesigning the system. From a risk perspective, it could involve risk of miscommunication or failure in one agent in the chain. For example, if the KYC agent incorrectly verifies a fraudulent identity, the error could cascade across the entire service flow. Hence, A2A implementation must therefore include fallbacks. It should have audit logs and human in the loop check for high risk decisions. Another concern is interoperability. That is, if different banks build proprietary agents which do not speak the same A2A, fragmentation could occur. Strategically, A2A sets the stage for autonomous customer service ecosystem. Instead of monolithic call centers, bank could deploy modular agent swarms that collaborate behind the scene. This enables personalized, efficient, and compliant services at scale. Over time, customer may not even realize that they are interacting with a network of AI agent. The experience will simply feel seamless, fast, and human-like. Let's take one more example of A2A. This time we will look at a case study of, say, smart city energy optimization. Now, cities worldwide are under pressure to reduce their carbon emission while ensuring reliable power for residents and businesses. Smart grid, solar farm, wind turbines, storage batteries, and dynamic pricing models are being deployed to meet these demands. However, managing such a complex system requires constant negotiation between different entities. Could be generation unit or storage facility or distribution network, and of course the consumer. Traditionally, this is handled by centralized system, but they often lack the agility to respond to real time fluctuation in supply and demand. Now, here is where A2A enters the story. The agent to agent protocol or A2A provides a way for specialized AI agent to coordinate energy management autonomously. Now, imagine a smart city where multiple agents operate. It could be a solar agent, a battery agent, or grid balancing agent, or say pricing agent. The solar agent monitors the photovoltaic output. The battery agent manages storage and discharge cycle. The grid balancing agent ensures overall system stability. And the pricing agents adjusts the electricity tariff based on supply demand dynamics. How does it work on ground? Let's understand the flow. Say one sunny afternoon, for example, the solar agent detects excess generation. Now, using A2A, it informs the battery agent about the surplus. The battery agent negotiates how much energy to store and how much to release back to the grid. At the same time, the grid balancing agent checks demand from residential area and industries. If there is oversupply, the pricing agent lowers tariff to encourage consumptions, perhaps triggering electric vehicle owners charging agent to start drawing more power. As an example, all these negotiation happens autonomously through a secure peer-to-peer A2A communication. The benefits are significant. Energy efficiency improves because agents continuously optimize resource allocation in real time. The cost decreases for consumers through dynamic pricing. The city reduces its carbon footprint by maximizing renewable energy use. Importantly, this decentralizes agent based approach, reduces dependency on a single central authority, thus making the system more resilient to failures. From a risk perspective, however non trivial, miscommunication between agents could destabilize the grid. Yeah, for example, if a battery agent fails to store surplus, While the solar agent assumes it will, it could lead to blackouts. Cybersecurity is another concern. Malicious actors could try to impersonate agent or inject false signals, causing widespread disruptions. Now, to mitigate these, A2A implementation must include strong authentication, fallback safety controls, and supervisory human oversight. Strategically, A2A positions smart cities to achieve sustainable, self optimizing energy systems. Instead of rigid central control, agents act as autonomous negotiators, ensuring optimal balance between supply, demand, storage, and pricing. Over time, such systems could expand to integrate regional or even national grids, thus creating a scalable, intelligent energy ecosystem. This showcases how agentic AI protocol can directly impact global sustainability goals. Agent Network Protocol ANP. Let's take an example from global supply chain logistic perspective. Well, global trade involves a complex ecosystem of stakeholders. Could be manufacturers, shipping companies, port authorities, custom agencies, insurers, and distributors. Today, supply chain often run on fragmented systems where each party maintains its own data. This creates inefficiency, increases the risk of fraud, and make it difficult to track shipments in real time. The 2021 Suez Canal blockage highlighted how fragile and opaque the supply chains can be. Here is where the ANP enters the story. The Agent Network Protocol or ANP offers a decentralized way for AI agents across different organizations to interact securely and transparently. ANP uses decentralized identifier or DID and JSON LED knowledge graph to establish trust identities and shared context. In a shipping scenario, multiple agents would need to collaborate. Example could be a shipping agent, it could be a customs agent, it could be an insurance agent, or it could be distributor agent at minimum. There could be more agents based on the complexity of your business. Now, a shipping agent represents the freight companies moving the goods. The custom agent handles the regulatory clearance at ports. The insurance agent manages the cargo risk and coverage. And the distributor agent could coordinate with warehouses and retailers. So, how does it work on ground? Well, a shipping agent transporting goods, say from Shenzhen to Los Angeles, registers its identity on the ANP networks. The custom agent at the port verifies the shipping agent's DID credentials and inspects the cargo manifest, all recorded immutably on the networks. The insurance agent negotiates dynamic coverage term based on real-time risk signals. When we say real-time, it could be say weather condition or piracy alert. Example. Meanwhile, the distributor agent receives trusted updates about expected delivery times, allowing the warehouse to prepare accordingly. The benefits are transformative. Transparency improves across the supply chain. Every party has access to a single version of truth, reducing any dispute. Fraud risk like counterfeit documentation decreases because all agents verify credentials via the did. Efficiency improves as agents automate negotiations, reducing manual paperwork and delays. For global trade worth trillions, even small efficiency gain translates into enormous economic value. From a risk perspective, well, here the risk involves interoperability and governance. Different countries may enforce different rules, and if some supply chain participate or refuse to participate in this case or to adopt ANP, we have a challenge. There are gaps in transparency would remain big challenge. Cybersecurity risk also exists. That is, if an attacker compromises an agent's DID, they could disrupt the system. To mitigate this, ANP network must enforce multi-factor authentication. They need to enable tamper-proof audit log and need to decentralize governance framework. Strategically, ANP could become the backbone of the next generation supply chain, a type of an internet. Just as TCP/IP standardized digital communication, ANP could standardize global trade interactions. It allows autonomous agent representing different organizations to trust, verify and collaborate without central intermediaries. In the long term, ANP enabled supply chain could be more resilient, efficient and transparent than anything possible with today's siloed system. Let's take one more example of ANP. This time we look at a decentralized healthcare research space. So, medical research, particularly for rare diseases, faces a major challenge. Data scarcity and fragmentation are a major challenge. Individual hospitals or labs may only have a handful of cases, making it difficult to conduct any meaningful studies. At the same time, strict privacy regulations like HIPAA or GDPR, DPDP prevents easy sharing of patients' data across institutions. The result is slower progress in discovering treatments for conditions that desperately needs a breakthrough. ANP enters the story. The Agent Network Protocol offers a way to enable secure, decentralized collaboration among healthcare agents. ANP uses decentralized identifiers or DID for identity verification, and JSON LD knowledge graph are used for structured, shareable context. This makes it possible for hospitals, labs, and universities to contribute data without giving up control or exposing sensitive patient information. How does this work on ground? Well, let's say a research hospital in Germany registers its research AI agent on the ANP network, establishing a DID that verifies its identity. A hospital in India has a similar agent that manages genomics data for rare disease patients. Using ANP, the German agent and the Indian agent negotiate a data sharing agreement. The Indian agent agrees to share anonymized, aggregated genetic markers rather than raw patient records. At the same time, an agent from US University joins the network, pulling structured insight to run statistical analysis. All the interactions are logged transparently on the decentralized network, ensuring trust among participants. The benefits are substantial. Research accelerates because data from multiple regions can be aggregated quickly without the need for a central authority or extensive manual legal work. Patient privacy is protected under ANP because it ensures that only pre agreed anonymized data sets are shared. Funding agencies and regulators gain visibility into who contributed what data, thus reducing fraud and duplication. For rare disease patients, this translates into faster discovery of biomarkers, diagnostics, and potential therapies. From a risk perspective, well, in this, the risk revolves around trust and misuse. Even anonymized data set could, in some cases, be de-anonymized if combined with external information. Rogue agents could attempt to join the network with fake credentials to siphon off sensitive research data. To mitigate this, ANP must enforce strict DID verification, zero knowledge proof for privacy preserving validation, and strong governance model that defines who can participate in healthcare research networks. Strategically, ANP could transform medical research into a global collaborative ecosystem where agents, not humans, negotiate data sharing deals in real time. So instead of waiting months for institutional agreements, researcher could access global insight within hours. This would not only accelerate rare disease studies but also enhance preparedness for global health crises such as pandemic. ANP thus lays the foundation for a new era of secure, decentralized medical innovation. Let's now look at cross protocol integration. We'll take a case study from autonomous financial advisory space. The financial service sector is undergoing rapid digital transformation. Customers expect personalized real time investment advice, while regulator demand transparency and strict compliances. Traditional wealth management involves multiple siloed systems, which include market data feeds, risk analysis tool, compliance checkers, and trading platforms. Even large financial institutions struggle to integrate this seamlessly. Enter the agentic AI, agentic AI with multiple protocols. Let's now mix together or work together. Here out how it likely works on the ground. Say a customer asks their bank's AI financial advisor for investment recommendation. The advisor agent uses, say, MCP to connect with Bloomberg API, market feed, and internal risk analysis system. The ACP is used to present information multimodally, which is chart, audio explanation, and text summaries. A2A is used to collaborate with other specialized agents like tax agents for tax efficiency and compliance agent to ensure regulatory alignment. And ANP is used to negotiate cross bank trade settlement, confirming identities and contracts through decentralized trusted verifications. The customer receives a personalized portfolio recommendation. Behind the scene, the portfolio agent worked with the tax agent to ensure investments minimizes capital gain taxes, and it worked with compliance agent to check suitability under the EU local laws or SEC rules in US. Once approved, the trading agent executes transactions across different financial institutions with settlements validated via ANP across international boundaries. The benefits are clear. Customer receives faster, more holistic advices, incorporating tax, risk, and compliance factors that traditionally required multiple human advisors. Banks thus reduce cost by automating back office functions like compliance checking and settlement negotiation. Regulators benefit from audit logs embedded within the protocol transactions, thus ensuring the required transparency. From risk perspective, the focus would be on the systemic impact. That is, if an advisory agent misinterprets data or if multiple agents miscommunicate, the customer could suffer financial losses. Cross protocol complexity introduces more attack surface. Hence, a compromised MCP connection to Bloomberg could feed on false data, or a malicious A2A agent could disrupt the collaboration, or a forged ANP credential could hijack settlements. In this, the mitigation could potentially include a human in the loop verification for high end value trade, or could include anomaly detection or strict regulatory auditing of AI agents' action. Strategically, this cross protocol integration demonstrates the future of finance. Fully autonomous yet compliant advisory system is what the future looks like. Customer interacts with one agent, but behind the curtain, a network of specialized agents coordinate seamlessly. This model could refine or redefine wealth management, democratizing access to sophisticated advices once only reserved for the ultra wealthy. The combination of MCPs, ACPs, A2As, and ANP shows how protocols together enable end to end financial automation, thus having the potential to reshape global banking. As this is a very critical topic, we'll take one more case study on how cross protocol integration can work. Let's take a disaster response coordination as a case. Well, when disasters strike, whether it's an earthquake, flood, or hurricane, the speed and the coordination of response effort can mean the difference between a life and a death scenario. Emergency response involves a wide array of actors. It could involve local police, hospitals, NGOs, logistic providers, satellite operator, international aid agencies. Traditionally, coordination has been plagued by delays due to fragmented communication or lack of real time data sharing, and more important, bureaucratic hurdles. AI agents powered by interoperable protocols offer a way to fundamentally transform disaster response. So let's look at how it would work actually on the ground. Well, the local responder or response agent connects to the IoT sensors. It could be seismic monitors, flood gauges, weather forecast, mapping tools, logistic database. Through MCPs, these agents fetch structured real time insight directly into their workflow. The agents share live drone footage, satellite image, streaming voice update across emergency team. For example, a drone agent streams video of a collapsed bridge to a logistic agent, which simultaneously share text-based alternative route options with the transport authority. Example, a rescue agent delegates triage information to a hospital agent, which allocates ICU beds in real time. Meanwhile, a supply agents collaborate with a warehouse agent to ensure that food, water, medical supply reaches the hardest hit zones, and they have to reach first. Each agent specializes in one task, but through A2A, they coordinate seamlessly. International NGOs, local governments, and foreign military support units each bring their own agent to the networks. Through ANP, agents validate credentials and establish trust without needing a central controller. This thus ensures that only verified organization can access sensitive coordination channels. Benefits: the disaster response becomes faster, more efficient, and more transparent. Instead of waiting hours for official report, decision maker receives instant insight. Suppliers are distributed based on real time needs, avoiding both duplication and scarcity. Medical triage is streamlined as hospital agents update availability continuously. Survivors benefit directly because critical resources and rescue team reach them sooner. From a risk perspective, disasters are high stake environments. Error could have dire consequences. If an AI agent miscommunicates the hospital capacity, patients could be misdirected. Cyber security is also critical. Malicious actor might attempt to impersonate relief organization to divert supplies. To mitigate this risk, protocols must be deployed with redundancy, strict authentication, real time monitoring, and more importantly, human override mechanism need to be enabled. From a strategic value perspective, this case study demonstrates how combining all four protocol creates a self-organizing, resilient emergency response ecosystem. It's a glimpse of agentic web applied to humanitarian context, which is decentralized, autonomous, yet trustworthy collaboration across the domains. In future, such systems could be pre-deployed globally, ready to activate instantly when disaster strikes, turning responses into a highly coordinated, agent driven effort rather than fragmented human scramble. In summary, MCP for tool and data integration, ACP used for rich communication and multimodality. Example is given was WhatsApp. A2A is peer to peer collaboration, analogy LinkedIn. ANP, decentralized agent ecosystem, analogy DNS. I hope this gives you a better perspective on these four protocols. With this, we have covered some part of the original agenda. We will end this part 1 and move to part 2 to cover rest of the agenda as on the screen. I'd like to thank you for the time that you invested till now. See you in part 2. This is your host Savit Vittal Salian. Namaskar.